This lesson will look at applying the inclusion-exclusion principle in a couple of questions and examples so you can see how it's used. So in this first example, we have a class of 25 students, and it says each of the 25 students study physics or chemistry, which suggests that there's none that don't study one or the other. 15 study physics, 18 study chemistry. So we should be able to say here that the universal set is 25. We should also be able to say that the number of physics students is 15, the number of chemistry students is 18, and the number of physics or chemistry students is also 25. Right, since all of them study. And that means that the number not physics and not chemistry is the same as physics or chemistry not, which will be 0. Now, if I was going to set this up in a Venn diagram, then that's very easy to do. The universal set, there's 25 students. We have physics, and we have chemistry. We don't know how many do both yet, so we have to calculate that. Now, if we use the inclusion-exclusion principle, we know that the number of physics or chemistry will be equal to the sum of physics, chemistry, and subtract physics and chemistry. So this is 25 is equal to 15 plus 18, take physics and chemistry. So 25 is equal to 33, take physics and chemistry. So physics and chemistry will be 33 subtract 25, which will be 8. So we've already answered the question. How many students will study both subjects? That's it there. If we want to draw this into a Venn diagram, we can say this middle value is 8. Now this is where we have to be careful because the sum of all of the physics students must add up to 15. So we can't put 15 here, that's wrong. It needs to be 7 here because 8 and 7 add up to 15. And for chemistry, this needs to be 10. 10 and 8 will add up to our 18. There's none that don't study either physics or chemistry. All right, so this should add up to our 25. We have 7 plus 8 is 15, plus 10 is 25, and there we have it. So hopefully that makes sense. A simple example, we've looked at creating that Venn diagram, but we've also looked at using that inclusion-exclusion principle to calculate. All right, now we'll look at a second example. So in our second example, we have a bag containing 100 balls with the numbers from 1 to 100. So we're going to say straight away, universal set has 100 values in it. How many ways can a ball be chosen that is a multiple of 2 or 5? Okay, so we're going to let set A be multiples of 2, and we'll let set B be multiples of 5. So that will be 2, 4, 6, 8, and so on, all the way up to 100. And this will be 5, 10, 15, 20, and so on, all the way up to 100. So here we have to think a little bit. How many values are in A? So if we think about that, it's every second value, and it must be 50. How many values are in B? So we have 5, 10, 15, 20, 25, and so on. So 2 for each 10. And so that means we end up with 20. Now, how many are both A and B? Multiples of 5 and 2 that cross over all the 10s, right? So that means we've got 10, 20, 30, 40, all the way up to 100, which means that we have 10 of those. Now, what this question is actually asking us is, how many ways can a ball be chosen that is a multiple of 2 or 5? So that means that we're asked to find what the union of A and B will be. So the union of A or B is the sum of the cardinality of A, B, subtract the cardinality of the intersection, which means we have 50 plus 20, subtract 10, which means that we end up with there being 60 ways that we can either get a multiple of 2 or 5. Okay, so hopefully that makes sense. That one is a little bit more complex because we had to consider the sets ourselves, determine the cardinality of each of the sets before we determined how many ways we could choose a multiple of 2 or 5. Okay, so example 3. So this example is pretty straightforward. We've got a class of 30 students. 12 enjoy cricket, and we're going to apply C there. 14 enjoy netball, and 6 enjoy both. So straight away, we can say that our universal set includes 30. The number of cricket is 12. The number of netball is 14. And the intersection between cricket and netball is 6. So straight from there, we can apply our inclusion-exclusion principle. We can say the union of cricket and netball will be cricket, netball, subtract cricket and netball. So that means we have 12 plus 14 subtract 6. That leaves us with 20. We know that the union is 20, and we should understand then that the cardinality of the universal set will be the union and its complement, which is not cricket or netball. So that means that we know that if this is 20, if this is 30, and this is 20, then all the values that exist outside will be 10. So we can easily turn this into a Venn diagram. So we have cricket, we have netball. Our intersection, which was given, is 6. We have 12 that enjoy cricket in total, so 12 takes 6 is 6. We have 14 that enjoy netball in total, so 14 takes 6 is 8. So 6 plus 6 plus 8 gives us our 20, and that means we have 10 left outside. And the cardinality of the universal set is 30, so that all adds up. So now we'll look at answering these questions. The number of students that enjoy netball only are, so this is netball and not cricket, will be 8. The number of students that enjoy neither cricket nor netball, so not cricket or netball, is 10. And then when we look at the probabilities, so part B1, we're asked to find the probability that a student will enjoy netball. So probability of netball is equal to the cardinality of netball over the cardinality of the universal set, which will be 8 plus 6, which is 14 over 30. And that simplifies down to 7 over 15. We look at part 2. We're looking at netball only, so we're looking at the probability of netball and not cricket. So the cardinality of netball and not cricket over cardinality of the universal set, which is 8 over 30 and simplifies down to 4 over 15. And then when we look at the third part, we're looking at both cricket and netball. So both cricket and netball will be probability of cricket and netball, which will be the cardinality of cricket and netball over the cardinality of the universal set. So both was 6, and we've got 6 over 30, which simplifies down to each of them are divisible by 6. So that's 1 over 5. So 7 out of 15, 4 out of 15, and 1 over 5 as our probabilities. So now we'll look at the second last example, example 4. We have a scenario where a card is selected from a standard deck of 52 playing cards. So this is saying that our universal set has a cardinality of 52. A is the event that the card is a diamond. So the number of possible ways we can get a diamond is 13. A quarter of the cards are diamonds. And B is the event that the card is a jack. So there's one jack for each suit. So B will be 4. So it's already, part A is asked us, what is the number of A? Number of A is just the cardinality of A, and that's 13. Part 2, what's the number of B? Number of B is the cardinality of B, which is 4. And then we're looking at the number of A and B. This is the cardinality of A and B. And so we're looking for all the possibilities where that jack is a diamond. Now, as there's only one of each card in each suit, the number of A and B is only 1. Now, for part B, we're looking to find the probability of A, and that means we're looking at the number of A over number in that universal set, which will be 13 over 52, or 1 on 4. When we look at part 2, we're looking at the probability of not A. So we're looking at the number of not A over the number in the sample space. So number of not A, if there's 52 in total, and A is 13, it will be 52, take 13 over 52, and that ends up being 39 on 52, and that simplifies down to 3/4. Now part 3 of B will be looking at the probability of A and B. So it means we're looking at the number of A and B over number in the universal set. So that will be 1 over 52. So there's a 1 in 52 chance of getting the jack of diamonds. Alright, so part C, they want us to use the addition rule to find the probability of A or B, and by that they mean the inclusion-exclusion principle. So probability of A or B is equal to probability of A plus the probability of B, subtract the probability of A and B. So probability of A is 1 on 4. If we go back up to think about the probability of B, it's going to be 4 over 52. If we put these all over 52, it'll make it easier. We've got 13 over 52 here. And we're going to subtract the probability of A and B. So this is 1 on 52. Then we're left with 13 plus 4, which is 17. Subtract 1 is 16 on 52, which is 8 on 26, and 4 on 13. So there's a 4 on 13 chance of getting either A or B. And when we finally look at part D, we want to find the probability that the card is a jack or not a diamond. So that means we're looking at B or not A. That means we're looking for the number of B or not A over the number of the entire sample space. So this is where it would have been handy to have a Venn diagram. So let's draw this Venn diagram out. The probability the card is a jack, not a diamond. So A and B. B is a number of jacks. We know that there's 1 that's a jack and a diamond. There's 3 that's remaining here that are jacks but not diamonds. And there's 12 that are diamonds but not jacks. Now that means that we've got 13, 16 that are jacks or diamonds. So that means there's 36 that are outside of these conditions. And if we're looking at B or not A, so that means B is this, not A is everything outside. So that means that we're just excluding these 12 here. So that means our probability will be 52 subtract 12 over 52, which means we have 40 over 52, 20 over 26, or 10 on 13 is our probability, randomly selecting a jack or not a diamond. Okay, so now we're up to the last example, and the last example is a complex one. How many integers from 1 to 140 inclusive are not divisible by 2, 5, or 7? So we're going to let A be divisible by 2, and so that will be a set that includes 2, 4, 6, all the way up to 140. We'll let B be divisible by 5, so this will be all the values 5, 10, 15, up to 140. And then C, B, divisible by 7. So this will be 7, 14, 21, and all the values up to 140. Okay, so we need to think cardinality of A. How many values are there? So every second value in 140 means there's 70 values. Cardinality of B, so there's 2 per 10, so that means there's 28. And cardinality of C, there's 2 lots of 10, which is 20. Now, when we think about the values that are both A and B, so the only intersections here will be the 14 and 28, so every even version. So that means that there's 10 that are divisible by 2 and divisible by 7. When we look at A and C, then it's only the 10s and 20s and 30s and so on, so that means there's 14. And when we look at B and C, it will be 35, 70, 105, and 140, so there's 4 there. Now, how many are divisible by all 3? So A and B and C. It can only be the 70 and the 140. So that means that there's 2. So how many are not divisible by? First of all, we'll work out what cardinality of A or B or C, the union at the center, will be. And that will be A and B and C, subtract A and B, subtract A and C, subtract B and C, and then add back in our A and B and C. So we have 70 plus 28 plus 20, subtract 10, subtract 14, subtract 4, and then add 2. So we have 118, subtract 28, and then add 2. So we end up with 92 that are divisible by 2, 5, or 7. The ones that are not divisible by 2, 5, or 7 will be the total amount, 140, subtract 92. So we end up there with 48. Okay, so there's a good range of scenarios there and questions to practice. You should be able to apply this inclusion-exclusion principle. You should be able to construct Venn diagrams, work out probabilities, and utilize the inclusion-exclusion principle, particularly with 2 sets, but working up to a higher level, looking at 3 sets as well. Okay, thank you for paying attention.